Welcome back, everybody. Today we are going to begin a series of lectures regarding relativistic mechanics. And this is a really fascinating subject because it's on the cusp of quantum mechanics in the sense that we're talking about particles, right? We're talking about, little itty-bitty things that are going very, very fast. And we want to think about them in terms of quantum mechanics, but we can't because we don't know quantum mechanics. We only know classical mechanics. And relativity theory is classical mechanics. Relativistic physics is classical. General relativity is classical because it has no quantum mechanical pieces to it. And today we are going to study the relativistic mechanics. We're going to begin a study of relativistic mechanics, and that will prep us for diving into what we are really excited to learn eventually, and hopefully you guys will find your way to the subject one way or another, quantum electrodynamics, which really is our precursor for quantum field theory in general, meaning quantum electrodynamics is where you start when you want to learn quantum field theory. And quantum field theory, of course, is what the standard model is all about, right? But relativistic mechanics is sort of a must-have step. And our typical place to study it in the curriculum is usually undergraduate electricity and magnetism frequently has relativistic mechanics in there because relativity, the relativistic part, flows pretty smoothly from an understanding of electricity and magnetism. And many professors cannot resist talking about relativistic mechanics once they're in the middle of E&M. I don't really believe it belongs there. I believe relativistic mechanics belongs in more of a modern physics course, where I put in quotes because what modern is a little bit hard to describe. I think my taste is modern means quantum. If you're dealing with quantum mechanics, you're in the modern physics era. However, there's an argument to be made that modern physics really starts with relativity. But regardless, I think E&M, understanding the Lorentz transformations, and it's just too big a block of subject to put in an E&M course where you're supposed to be studying fields and waveguides and the propagation of light and potential theory and all those cool things. So I feel like it's too much of a block to belong there, and it really does belong in its own class. Anyway, we're going to treat it on its own terms. And why are we going to do this? Let me give you an example of where in QED this stuff shows up. I've pulled this photograph out of one of my favorite textbooks, An Introduction to Quantum Field Theory by Michael Peskin and Daniel Schroeder, commonly known as Peskin and Schroeder in the biz. And here you have this is a purely quantum mechanical construction right here. It's the electron vertex function, a wonderful calculation. It's been so long I forgot how it works, but you can take this Feynman diagram and you can turn it into this integral right down here. But the point I want to call your attention to is this thing, k minus p squared. That's the difference of two four momentums squared, which means it's a number. It's the magnitude of the difference of two four momentums. And you'll see k squared minus m squared here, which is the difference between an invariant, a scalar version of a four momentum, that's k squared. This is an invariant term. We'll talk about that in a moment. And m squared, of course, is an invariant. And you'll see that these things show up all over the denominator of this, k prime squared minus m squared. You'll see an m squared up here. Interesting, you have a gamma mu there, which is a Dirac delta matrix, and then you have these slashes. But they all sort of go into the four momentum. Everything here is four momentum. Now, in the QED, of course, this thing here, in QED terms, this guy here is a spinner, actually. This is a set of Dirac matrices. So there's more here than just pure four momentums, don't get me wrong. But the idea is this diagram is built out of four momentums. And the difference of four momentums, the sum of four momentums. This is the flow of four momentum into the diagram. This is the flow of four momentum within the diagram. This is the flow of four momentum leaving the diagram. So having a really good sense of how this, and all of those four momentums are guided by the subject of relativistic mechanics. And so understanding that really well before you approach these things in QED is super important. And so that's what we're going to study in this class. Also, I want to point out that these Dirac matrices are given by gammas. I don't want to start some confusion now. Gamma mu is a Dirac matrix, but we're going to use gamma in a different way. This is going to be the Lorentz factor, and it's unrelated to this gamma mu, as you'll see in a moment. Okay, so that's the motivation. Let's begin. We'll start with our conventions and units that will define all of our work. And the first thing I want to make clear is we are going to be dealing with 4 vectors, right? And 4 vectors have the time component, which is given by a little 0. The 0 component is always the time component in our work. And the space components have I equals 1, 2, and 3. So I can be 1, 2, or 3. And together, they're bound together as a 4 vector. And we'll typically write that 4 vector as x mu. And this is the contravariant form of the 4 vector. Now, if that doesn't mean anything to you, if you don't understand the contravariant form of a 4 vector, then this lesson is a little bit too far down the road. You got to kind of go back and bone up on your basic relativity theory and the mathematics that is used to construct it. We will be reviewing it here, but if that means absolutely nothing to you, then this is probably a little bit too much. This is a bit of a math check, I guess, in the parlance. But the first 4 vector, the 0 component of the 4 vector, is always called the time component, And in a position 4 vector, like I've illustrated here, the time component is the speed of light times its time coordinate. And the space component would just be measured in units of distance. Now, overall, we are going to eventually have c equal to 1. It's going to be unitless. And all of the components will be measured in terms of just distance. Okay, so then what is our metric? The metric that we're going to use is the mostly negative metric. Let me fix this little 0 here. The mostly minus metric, they call it, mostly minus, because the space components of the metric are -1 and the time components is positive. For those of you who track through a lot of our general relativity work in this channel, we use the opposite convention for general relativity. And overall, I think that's the pattern. Particle physicists and relativistic physics is usually done in this mostly minus convention, and general relativity is usually done the other way. And then this metric, of course, will be used for raising and lowering operators. This is our convention for converting a contravariant set of components to a covariant set of components, likewise covariant to contravariant. And because of this mostly minus convention, what that usually means is that the time component does not change when you go from covariant to contravariant, but the space component picks up a minus sign. So that's the convention we'll be using for our 4 vectors. And now let's talk about one 4 vector in particular, the momentum 4 vector. All 4 vectors can be squared, and squaring it means contracted with itself. This is an Einstein sum, so you'll get P0, P0, minus P1, P1, minus P2, P2, minus P3, P3. Those minus signs come in from these minus signs of the metric, and ultimately from this fact for all 4 vectors. All 4 vectors have to have that same introduction of the minus sign when you contract it with itself. And we'll see an example of this specifically for momentum in a moment. But this guy here ends up being a scalar. This is a number, right? This is the sum of 4 numbers. And ultimately, this is a number. And because of that, this thing is invariant, right? Invariant, meaning it just doesn't matter whatever rest frame P is in, whatever, you can switch rest frames all day long, transform P as required using Lorentz transformations, but when you calculate this square, it will always be the same. And we'll look at that a little more closely at item number 5. But if this final invariant number is greater than 0, we say that this 4 vector is time-like. If it's equal to 0, we call it like-like. If it's less than 0, we call it space-like. All right, so that's our convention for the contraction of a 4-vector. And then our gamma matrix, I was about to call it a gamma matrix, wasn't I? See, I almost fooled myself with these Dirac matrices. No, the Lorentz factor, right? The Lorentz factor is given by this expression, 1 minus the 3 velocity squared. Now, this is a 3 velocity, right? So I almost should put it like, well, I've done it here, right? V in this Lorentz factor. When you see a V in the Lorentz factor, you always think it's the magnitude of the 3 velocity, right? And I put the little minus sign in red there because I always forget, and I sometimes leave that out. And I actually, when I first wrote this, I noticed I dropped that minus sign. But it's minus 1/2, so it's 1 over 1 minus v squared. Now notice here I have v squared, but I don't have v over c. Right? I don't have this, v over c squared. That's not the way I've written it. And that's because I have already made the assumption that the speed of light is a unitless quantity and it is equal to 1. Therefore, all of our velocities, if that's the case, will be greater than or equal to 0. I should have an equal sign there. And it will be less than 1, less than the speed of light. And that, so this is a natural units convention, a convention of natural units. And let's see, is there anything else important? Oh, yeah. So then Lorentz transformations, from time to time, we might have to indicate a Lorentz transformation, which means we're taking the components of a 4-vector and we're finding new components, and those new components are in some other rest frame, and the difference between those rest frames is one Lorentz transformation. So the Lorentz transformation is represented by a matrix. That matrix, in this case, will be lambda. And you'll notice my favorite convention is a convention used by one of my professors back in grad school, and I liked it the best. I don't see it all the time out there, but I think it's the best convention. What we're doing to indicate the new reference frame is we put a little prime on the index. So this is now the prime frame. And that's why I like it. You can say this is the unprimed frame, this is the prime frame. And you can convert either way, right? You can go one with the other, just, they're symmetric in the sense that they're both legitimately physical, totally legitimate frames. One is just carrying around this decoration of a prime, but this just tells you you're in the unprimed frame of the prime frame. Now, the other alternative ways of doing it is like putting a bar over it, saying that's the barred frame, or even really weird, you could go like x prime nu or something like that, which is terrible. But this is my favorite. You actually keep the index the same, but you add the little prime. And then your Lorentz matrices have indexes that are unprimed and primed. And then you just sum over the unprimed one. They're totally different indices. This might as well be like an alpha, and in this case, this would ultimately be x alpha after you've done the sum. Fair enough, but you have to indicate it's on the prime frame. So it would be like x bar alpha, and that is typical, that is done, but it's not how I'm going to do it. So that is what we're going to do for our Lorentz transformations. And then this is just a rule for Lorentz transformations and their inverses is this delta function, which the Einstein sum is over the mu's. Now, for the time being, I am not going to go into how to construct this matrix. We've done that in other classes in this lecture series. It's a bit esoteric, and we don't use it quite as much in pure relativistic mechanics as we do in field theory. But it is important to know that any 4-vector can be transformed from the prime to the unprimed frame using a Lorentz transformation. Okay, and now let's talk about one particular 4-vector that is so important. We're going to talk about the momentum 4-vector. And the momentum 4-vector in its contravariant form is often written like this, where this p with the arrowhead is really supposed to be pi. And that's probably better to do. I probably should take this, to get rid of this, and then go with an I here like that. But it's often written PPI Otherwise, another way that it's pretty commonly written, actually, I have yet to, I'm getting a little bit ahead of myself, but it's also written E, P vector like that, right? That's another very, very common form where, because P0 is always the total energy of the particle and Pi are the components of the three momentum. But it's a four vector, right? So the four vector is the basic structure of relativistic mechanics. Everything that's meaningful that's not a scalar is a four vector. And indeed, a lot of scalars are just four vectors that are contracted with themselves, right? But the point is when you look at a four vector, this is the thing that when people say, oh, Einstein put time on the same footing as space, which is a really vague and kind of meaningless statement. Like, I mean, if you're trying to explain this to somebody who doesn't know physics, he put time on the same footing as space. There's no way to process that. But if you said, oh, he showed that time and space were really the same thing, or that's not right either. I'll show you why in a second. But it is true to say that Einstein took time and space and bound them together in a single object, which is four vectors, all kinds of four vectors, spatial four vectors, like position four vectors and momentum four vectors. All these four vectors for things to do with electromagnetic field, they all have a time component and a space component. And every physical theory has to work ultimately with invariant quantities, and invariant quantities are four vectors. They're almost always made of four vectors at the level we're going to be studying. And so they're bound together, right? Time and space is bound together in these four vectors, and that's what they mean just by saying on equal footing. You can't deal with space on its own. You must include time in the same thought processes or the same analysis or the same model that you include space. You can't separate them. The only way you can separate them is if you go to certain regimes of physics where the distinction or the binding doesn't matter as much, and you would concede that you're just approximating things, right? So these four vectors, momentum four vector, the first component is the total energy. The second component is the three momentum. And the square of a momentum four vector is the contraction of the four vector with itself, and it's given by this expression. These negative signs come in from the fact that you're contracting a covariant with a contravariant piece, or a contravariant with a covariant piece, and to do that, the covariant piece picks up these negative signs, so that product has the negative signs, but the covariant part, the time part, the 0, 0 piece, doesn't pick up the negative signs, so it keeps its positive part. So to say that time is handled the same way as space is not exactly correct either, right? Time is still distinguished because it doesn't pick up this negative sign, and that has huge implications for this theory. So time and space aren't literally the same, and this is often sort of said when people describe relativity theory or relativistic mechanics. Time and space are somehow bound together and the same, but they're not. And time is not just another spatial axis, and this is exactly why. But regardless, when you create this scalar, and this is going to be a number, right? These are four numbers: one number, two numbers, three numbers, four numbers. You subtract these three from the first one, and you end up with a number. And that number is invariant. Doesn't matter what reference frame or what rest frame the observer, are in. If you have a four vector and you transform it to any frame and you calculate this quantity, you're always going to do this calculation. And each of these numbers are all going to be different regarding the frame. But when you perform this sum, it's going to add up to be the same thing. And that same thing we call the rest mass. And so ultimately, E squared minus the magnitude of the 4 momentum squared equals the rest mass. So this is a very important relationship that we'll be using a lot. And in addition to this 3 momentum is defined as the gamma factor times the rest mass times the velocity. This is actually more of a definition of the 3 velocity, right? So this is an important little relationship. And now we're going to take these relationships and we're going to come up with a very important way of understanding the gamma matrix. I said gamma matrix again. The Lorentz factor, So here I've kind of worked it out in advance, right? Here's just the definition of the Lorentz factor, right? This is derived through, essentially, the way I saw it derived through was ultimately electromagnetic theory. You'll notice that V does not have, just to be super clear, V is not V over C like you often see it in more elementary treaties where they don't shift the units to C equals 1, because that's actually pretty weird, right? A velocity is now a unitless thing. It's a little bit too much for super elementary physics. So often you see this C down there. But we're big students now, so we don't need to do that. And this is the definition of gamma. However, it's not a very intuitive definition of gamma. So let's find a more intuitive definition for gamma. And we start with our expression here, that the invariant momentum, this invariant term, the rest mass, right, is equal to E squared minus the 3 momentum squared. But we have this rule for what the 3 momentum is, so we can get the velocity, the 3 velocity in there by making this substitution. And then we get a gamma term sitting in this, and we're going to solve for that gamma. So we take this guy, we square it, we put it right here, we take m and we move it to this side, and we take this p, we substitute this, and we move it to that side and square it, right? So we have to square it. And then we end up with this expression. The difference between the total energy and the rest mass is equal to this object. And so now we're going to substitute out for gamma squared, and hopefully that'll deal with this v squared somehow. So first thing I do is I divide by m squared. Let's see, hold on a second. I divide everything by m squared. So this becomes a negative 1, and this just goes away, right? I move that negative 1 over here to get a positive 1. There's an m squared now under the e squared. So I get this v squared, 1 minus v squared plus 1. And that 1 minus v squared came from the gamma squared. I have to substitute for gamma as well. So I get a 1 over 1 minus v squared. And then it's just a bit of algebra. You put everything over like fractions. The v squares cancel. You get 1 over v squared. And you recognize that 1 over v squared is gamma squared. And so now you have E squared over rest mass squared equals gamma squared. And that leads to gamma squared is the ratio of the total energy to the rest energy, which is really cool. That's a very insightful and useful way of understanding gamma. And for very, very high velocity particles with a lot of kinetic energy, E is going to be huge, many, many, many more times bigger than the rest mass, and gamma will get quite large. However, if you're totally stationary and there's no kinetic energy, the total energy is just the rest energy, and you get m over m, which is 1, and gamma equals 1. So it's really, really a great method, or a great method of thinking about the Lorentz factor. But this is our first sort of example of the kind of algebra that we'll see a lot in this course. It's not super hard. It's all purely algebra. But, every now and then you got to remember something, right? Like here you have to remember, oh, wait, 1 over 1 minus v squared. Isn't that just the square of gamma? You got to remember that. And hunting down this process and getting through this to get to this relationship, it's not that intuitive, but it's not that hard either. In other words, if I just asked you to find a really simple relationship for gamma, it's not clear that you would immediately think to do this. You'd be hunting around and nothing presents itself obviously. There's enough depth in the algebra to obscure what the result is actually going to be. I guess that's the best way to say it. Okay, so now what do we want to do next? Now, it is my goal to keep these lectures to within a half an hour now. I'm going to change. Most of the lectures we've done in this channel have been more like an hour long. I want to tighten things up a little bit. They're easier to produce that way, and they're probably easier to consume. So our next topic will be particle decay, but we're going to look at this totally without quantum mechanics. So we're not worried about the cross-section for decay or the quantum mechanics of like escaping a square well or something like that. We're just going to understand the pure, I guess almost just the pure kinematics of a particle decay. And we're going to use a really great trick that we use time and time again. We're going to go into the rest frame of a parent particle that's just sitting there, just motionless with its rest mass and zero momentum. And we're going to try to understand what can we learn about the momentum four vectors of the decay products, which are often called the daughter particles, but the children particles. And we're going to use some basic relativistic physics to do this. And you're going to see right away that the algebra can get pretty messy even for the simplest situation. So that'll be our next lecture, and that will begin our journey into deeper and deeper and more convoluted but relevant relativistic mechanics. So I'll see you next time.